Okay, so let's talk about waves interference topics. So an interference pattern just occurs when waves from different sources arrive at the same point at the same time. There's two different types of interference. There's constructive interference, and this just happens whenever a crest of one wave overlaps a crest of another, and a trough of one wave overlaps a trough of another. And this creates reinforcement where you've got a wave that's produced of the same frequency, but look at the amplitude. The amplitude now adds together. Destructive interference occurs whenever the crest of one wave overlaps the trough of another, and the trough overlaps a crest, and you end up with cancellation. So what ends up happening is the waves just cancel each other out. They add up, and like if this was +1 and that's -1, well, +1 minus 1 is 0, and that occurs over the entire length of the wave. So if you have this happening over and over again, then you have what's called out of phase and in phase, especially if the waves are not exactly the same frequency. You'll see this develop. But even in waves that are the same frequency that originate from different spots, you'll still see this develop. You'll see this in water. You can see that we have high points and low points, and the high points correspond to constructive interference, and low points correspond to destructive interference. So the areas that are destructive interference are also called out of phase, and the areas that are constructive interference are called in phase, meaning the crests are meet the crest, and you end up with reinforcement. So what is a standing wave? So standing waves form only if half a wavelength or multiple of half wavelengths fit exactly into the length of a vibrating medium. And you saw this whenever we were doing waves on a string the other day. You saw standing waves, and of course standing waves have both nodes and antinodes, and we've been through this. Make sure you mark this on your paper, the nodes and the antinodes. Make sure you also leave plenty of room to go ahead and have the different parts of the wave easily visible for you, okay? So incident waves, that's just the wave as it's traveling from the source to a boundary, and the reflected wave is after it's hit the boundary and is reflected back. Now you can see, like right here, you have the crest, meaning the trough. So what's going to happen there? Well, it's going to be out of phase. It's going to have destructive interference. What you need to keep in mind is that standing waves are a result of interference. You have both constructive and destructive interference that occurs. And where you have the antinodes, well, that's constructive interference. And where you have the nodes, that's destructive interference. So standing waves are set up in musical instruments. For instance, a piano, the strings in a piano, or in air and an organ. Standing waves can be produced in either transverse or longitudinal waves. So I want you to listen to this from the perspective of the observer of the camera, and then they're going to show the perspective of the driver, and it's the same exact time. So I just want you to listen to the different perspectives. Of course, it's in two different parts of the video. So
again, you might realize that that's maybe not a bad place to be.
Catcher with Piaffoni working him. Right back in the field. Actually back.
There's the camera right there. Okay, so you heard wherever it was perspective of the camera, you heard a where it was going high as the car was coming towards you, and then it went low. This is called the Doppler effect. This is the apparent change in frequency due to motion of the source or receiver. And the greater the speed of the source, the greater the Doppler effect will be. The Doppler effect causes the changing pitch of a siren or a race car. When an object approaches, the pitch sounds higher than normal because the sound wave creates waves that are more frequent. So you're basically driving into the sound waves, pushing these waves together, giving them a shorter wavelength, which a shorter wavelength in a medium, because velocity equals frequency times wavelength. Well, if wavelength goes down, velocity has to stay the same. That means frequency goes up. So the observer is hearing a higher frequency because the waves are pushed together, and then they pass them. Now the source is driving away from, the fire truck's driving away from the waves, therefore spreading them out. And again, now the wavelength gets longer, frequency goes lower, and that's a ooh sound in a race car. So, and obviously, if you went back and you listened to it, the race car driver just heard the sound of the car the entire time. Police use the Doppler effect of radar waves to measure the speed of a car on highways. Radar waves are electromagnetic waves, just like those that are in your cell phone or in your microwave. Police bounce them off of moving cars, and then a computer built in the radar system compares the frequency of the radar with the frequency of the reflected waves to find the speed of the car, because the reflected wave, just like with a race car, will be whenever it's bounced off, if the car is moving toward them, then those waves will be shorter increase in the frequency. So all the electronics has to do is compare the original wave wavelength to the wavelength being reflected. So the Doppler effect has a lot of implications with astronomy. An increase in frequency is called blue shift, and this just means that whatever planet is, if we're expecting to see a certain color and we know that color has been shifted to the blue end of the spectrum, then we know that that star or wherever we're looking at is shifted toward us. And there's a whole lot of chemistry that goes in that's involved in knowing what color we know should be there. It basically means that, hey, look, we know that a star is made out of, certain elements. And if it's in the spectrum, then it's got to be these elements, and we're expecting this exact frequency, and we can see that frequency isn't what we're seeing. We're seeing one that shifted just a little higher than that. Well, there's no natural element. There's no elements that would have that particular frequency whenever it's excited. So we know that because it's shifted toward the blue end of the spectrum, then that star has to be moving towards us. And vice versa, we see that a decreasing frequency is called redshift, and this refers to the low frequency or red end of the color spectrum. Distant galaxies show a redshift in their light. This measurement of this shift enables astronomers to calculate that their speeds, that they're rescinding from us, they're moving away from us, and this helps us understand that the galaxy is still in expansion. It's getting bigger, which is really, really neat, and it gets some really big questions. Why is the galaxy expanding? Where, and then you get into, well, what's making it expand? And there's got to be extra mass out there, or extra energy, and that gets into dark mass or dark energy, and it's like, it just gets more and more questions. And probably they're going to find these answers out someday to be something simple, but, right now there's still a lot of questions. Okay, so if you've ever been in a boat in a lake, then you've seen bow waves. These are the waves that just travel away from you. And, just like with a string, there is a speed involved, and that speed is set by the medium. And of course, the medium in water is the water itself. You can't go faster than the waves. Well, you can go faster, but the waves can't go faster than that set speed that's for water. Now, what's interesting is whenever you do go faster, a few years ago, I went out on Texoma with a friend of mine, and I can remember whenever he started, he was on a speedboat. Actually, he was on a bass boat, but he thought it was a speedboat. Somehow he ended up going about 80 miles an hour in a foggy day. It was really scary. But as he started hitting those waves, I felt the boat start really getting, super bumpy, and then all of a sudden he got, faster than that, and the boat just completely glid on the water. It was really, really neat. So what was going on is he got out in front of this bow wave, and he got into smooth water. He was no longer moving on top of the waves he was producing. So this is called a bow wave, and of course it is a type of shock wave, and this occurs whenever an object moves faster than the speed of sound or the speed of the wave that's in that medium. And it's a three-dimensional wave that consists of overlapping spheres that form a cone, specifically with sound. The conical shape generated by a supersonic aircraft spreads until it reaches the ground. And of course, we sense this whenever something's going faster than the speed of sound, then we see this, or we sense this. We don't see it. Sometimes, depending on the humidity in the air, you can see what's going on, but you sense this as a sonic boom. And this is just the sharp crack heard when shock waves that sweep behind an aircraft reaches the listeners. This is most often considered associated with a jet aircraft. However, people that have been shot at with bullets, they have said, "Oh, well, I heard the crack of the bullet." Well, that crack is the speed of that shock wave. And I remember a few years ago, I was telling a group of students that, and he goes, "Yeah, I heard that one time." And I was like, "What?" And he says, "Yeah, I was being shot. I got shot, and I can still remember the crack of the bullet going, one of them going by me." And I was like, "You weren't shot." And he showed me the bullet hole. I was like, "Wow, wasn't a hole then, but he showed me where the wound was." So a common misconception is that sonic booms are produced only at the moment that the aircraft surpasses the speed of sound. That's not true. It constantly goes behind the plane. So for instance, when this shock wave reaches A, he's going to hear it. He's already heard it. Now it's reaching B, and this guy over here at C will get it. It just hasn't reached him yet. So that's going to constantly being swept behind him. So there are other types of shock waves. This is, we've heard the story where I just heard a supersonic bullet passing over somebody. You can hear the crack of the bullet. And then, of course, if you've ever used a whip or seen somebody with a whip, whenever that whip cracks, that's caused from the whip getting faster at the very end than sound and the speed of sound, and we hear that as a sonic boom. You can also do this with a towel. So, okay. Well, I hope this helped you, and I will talk to you guys later. Bye.